see this sign, do you like to take things apart? Raise your hand. We're going to get started. I'm going to start at the beginning of this. Mr. Detoy, Tom Detoy's going to introduce himself too. He'll be jumping in and probably finishing this thing up, as we'll be team teaching this year. Kind of, Tom does such a great job. Really want him on board. So you're going to get his perspective on Wednesdays. You're going to get my perspective on Mondays. We will have seen the videos, and many times I will listen in on Tom's, so we can really tag team this and do a good job. So really excited about it this year. So just so you know, we're always recording the webinars. I'm recording it now, so everybody understands that. It's very important, though, as much as possible, to come to these webinars live. You're going to get so much more out of it. So I really would encourage, I'm going to put everybody's hands down now. To come to these live. We will record them. They'll be there, but it's best to come live. So if you like to take things apart, if you're curious about how to solder, many of you have, because you're in the 5th and 6th grade program with us before. Maybe you were in 7th grade. But now we'll even do more soldering this year, and a little more demanding soldering. You're using epoxy. Can you repair a tent with a needle and thread? Those kind of ideas. Do you like science fiction or fantasy? All those things, then you're in. Welcome, because you're among friends. All right, we got 11 questions here. Let me see who it is. Oh, it's Kevin. Hey, Kevin, I hope you're doing well. You have one? Yep, great. All right, it's going to be going back and forth on this. All right, now, about us. I'll introduce myself. My name is Mr. Dubick. I've been teaching engineering to young people and science for 30 years. It's my 30th year of teaching, and I'm very excited about it. If you look down at this bottom picture right here, this is a group of students when I was just first teaching. Hey, yes, I didn't have gray hair then. This gentleman's a minister. This person is a engineer. She's a scientist. Not sure what happened to him. A couple of these are business people. We made the world's largest paper airplane at the time. We are a Fablab. We're excited about what we're doing at the Fablab this year. We've been learning a lot at our end. We got more things to share what we're going to be doing at the Fablab. So you'll either come out on Thursdays or Saturdays. Next Thursdays, you're in first class. This Thursday will be the high school kids. I graduated, undergraduate was Ohio State. Graduate school was at UNC Charlotte, and I co-founded Young Engineers of Today. Tom, take it away.
Well, hello, everybody. My name is Thomas Detoy. You can call me Mr. Detoy. You can call me Thomas. You can call me whatever. I was born in California.
As I was. I was born in Fresno. Where were you in California?
Oh, I was born in Huntington Beach.
Oh, that's a much cooler place than Fresno.
I know Fresno's pretty neat too. California's pretty neat all over. I've studied computer science at UNC Chapel Hill, and currently I am a full stack and C developer, which is a little bit weird, but I work for a pretty small company, so I get to do a whole bunch of stuff, including like server maintenance and stuff like that. Hey, caveman. Full stack just basically means I work on the front and back end of websites, among other things, and do a lot of web stuff. It's pretty interesting, actually. Not something I anticipated that I would be getting myself into, but I really enjoy doing it. And that's the funny thing about life. Sometimes it takes you in funny directions. So that's what I do. And I'm actually going to, let's see here. Oh, yeah. Thank you.
I moved you.
As far as interests are concerned, I like coding of all types. I like electronics. I like taking stuff apart, seeing how it works. I like looking at the back end of things, seeing what exactly makes it tick. I think it's a lot of fun. I think it's really interesting to see sort of what goes through other people's heads. I've developed some, yeah, I am. I've developed some small applications in Python and C and C++, and as well as Java and the Android framework, which is basically Java, just with some XML sprinkled in it and stuff like that. And I've worked for Young Engineers of Today for 3 years now. Actually, this would be the start of my 3rd year of teaching. So
you're actually, yeah, I think you're even there longer than that. actually.
It could be. Yeah, I know. I know. I helped out. I know I helped out Mr. Pearson when he was starting the Minecraft stuff. And yeah, pretty weird. But I mean, we kind of all are to some degree. So let's have the fun, right?
Agreed. Normal's way overrated.
Yeah.
All right. I'll jump in. Do you want to explain what we're going to do on the webinars, and I'll explain in the lab, or how would you like to handle the time? Oh, let's get through this minutia. Let's do this first.
Okay.
All right. We have Edmodo codes. I need everybody to take a moment right now. If you're not already registered on Edmodo, get involved. So these codes, we're going to put, when we try to get the word out to you, we're going to put it both on Edmodo or YouTube. This is our way of emailing you. We much prefer you talk to us through Edmodo when we can. So, you see this code? You've got to log in. Make sure you're a student. Don't log in as a teacher, and go in as Edmodo. They're going to ask for a code. There's your code. And then you'll be a member on Edmodo. All right? So for everybody, it's this code that is watching the webinar right now. It's this one right now. If you've gotten that done, go to our YouTube channel. Subscribe to that. I'm going to put this in the chat so you can just click on this link. All right, let me go ahead and set a chat window here. Bear with me 1 second. Oh, shoot. Come on. Correct answer here. I'm going to send this to everyone. Let's take a few minutes right now. You should chat. You should see that link. This way, all the webinars are going to get posted. We're going to try really hard to get these all posted. If not that night, first thing in the morning. But so that way you can get to these. If it doesn't post, it's because there's a problem. We had some kind of technical. We'll try really hard to post these, but we cannot guarantee that we're going to have every webinar recorded. We'll try real hard, but that's not a guarantee. Someone has a hand up. Yes, Luke. Did you mean to have your hand up, Luke?
No.
All right, I'm going to mute you back down. No worries. Kedman, what you need, buddy? Hey, Kedman. I'm going to go ahead and mute you back down, and I'm going to put down everybody's hands again. Aiden, got to get here. We're just getting the introduction, Aiden, but please get here on time. It's real important. And Aiden, we're stressing really important that you come to all the webinars live. Here's the Edmodo codes for you, and here's the YouTube. Let me also explain, to be fair to the people that come every time, if you miss a webinar, it's up to you to go through the webinar. We can't reteach it. We can't take class time to spend 20 minutes of class time catching you up when everybody else was here. I want to stress that. We really need you here this time. Everybody's time is just as valuable. So, please come on time. Please attend the webinars. Watch the webinar. A question's fine, of course. We don't mind answering that. But we can't say, well, I missed the last 3 weeks, last 3 sessions. You got to bring me up to speed. It's not fair for the other kids that are here. All right. Luke, you've got your hand up. I'm going to unmute you, Luke. What's up, Luke? Hey, Luke.
What? Hey.
Do you have a question?
No.
All right, then let's put our hand down. We'll use that that's okay. We'll learn how to do it tonight to practice all these things. So, please, everybody, I'm going to ask in a minute to raise. We got hands going up and down. Let's put our hands up right now if you have a question. So, Luke, I'm going to take your. Let me do this. I'm going to put everybody's hands down. Put your hand back up if you have a question right now. All right. Luke, what's your question?
Wait, do you keep it up if you don't want a question?
You keep it down. I will lower it. Only put it up if you have a question. Cademan, do you have a question?
Yeah.
You got to speak up, buddy.
I don't think you can.
I can't hear you. Cademan, got to turn up your mic or something, bud. Can't hear you. Now that sounds better. What's up?
Can you hear me?
Yes. What's your
thanks.
question?
Detoy, you
It's Mr.
worked with
Detoy.
Notch? Mr. Detoy, you worked with Notch?
Oh no, I've worked.
In person, so.
Oh right, no, different Pearson. Ah, yeah, no, I can totally see how that would have happened. Yeah, no, not
Yeah.
Marcus. Decidedly
Your
more.
first name turns with Notch. Oh my God! Your last
All right. Okay, well, I'm glad. I made him make Cademan happy and impress Mr. All right, guys, here's what I'm going to do now. Raise your hand if you've gotten your Edmodo code registered. Please raise your hand. All right, we've got a couple that don't show it. Leave your hands up, guys. Please don't put your hands down. I will lower your hands. Please leave them up. I beg of you, please, please, please. So this way we can figure out, because I still show 4 people here who don't have their hands up. It's not to embarrass you or anything. We just want to make sure if you've gotten it done. Jada, do you have it? Luke and Ashlyn, do you have, and I might have your parents' names here. Sorry about that if we do. But let us know. Either raise your hand because you found your code, or chat with me, or write us an email that you couldn't get the Edmodo code or you need a hand. You just go to edmodo.com. And then kids, and that way also you can have your parents use the same code to register for them. I knew Mike, no worries there, Kevin. Also, I'm putting everybody's hands down then. How many people have subscribed on our YouTube channel now? Raise your hand once you've done that. So let's get that done. There should be like 250 subscribers. We have over 1,000 hours of webinars videos, I think, by now. Oh, we have a lot.
Wow.
Raise your hand once you've done that, because we really can't go forward. We want to make sure we get all of this done. So we only have about a quarter of you guys registered on YouTube. Let's do that right now. You can jump off the other screen, go to YouTube, and just so you're subscribed to it. That way you'll get posts when we post a new one. Getting there. Leave your hands up. Don't take them down once you subscribe. That way we know how many people are signed up there. Once you get about 70%, we're going to go on, but it's up to you all. Kevin, make sure you've subscribed to YouTube. Luke, unfortunately, Jada, if you can, subscribe as well. Raise your hands, let us know. All right. We're going to go ahead and go on from here now then. So what we are going to do is what we've been doing all years. Both Thomas and I have been doing this. Tom and I have been doing this. Mr. Detoy, you're going to be working with your head and your hands. I promise you. We want you to get comfortable and work ourselves out of a job. If that makes any sense at all. We as teachers want to teach you how to do it so they don't need us. You can go on and make your own cool stuff. And we want you to work on problems that are, as we work on these projects, we're hoping you work on things and these are relevant and make sense and interest. We rarely, in fact, never have had someone in an engineering class say, why do I need to study this? And Mr. Detoy does a great job with, particularly in programming. He's a super strength. And I think Tom would say, I want you to learn how to code.
Yeah. It's not just useful for the actual knowledge itself, but it's how you think, which you can apply to many different places in your life anyway.
I really think code in some ways poetry. As you get better and better, it gets elegant. It looks nicer and looks clean. And
yeah, you can really appreciate sometimes some of the code you've written and some of the code other people have written.
Absolutely. All right. Tom, do you want to talk about the webinars, or do you want me to jump on that? It's fine with me.
I can grab the webinars.
All right, I'm going to give you a little. I'm going to give you the keyboard mouse. Let me see how I do that. Staff here. Let me see.
Oh, here I can do that.
Oh, okay.
Boom.
I think I might beat you to it, but by the time you said it, already clicked. See if you can get the mouse. It's not doing it yet.
Looks like I do.
You got it.
All right. So yeah, as far as webinars are concerned, we're going to be covering the Raspberry Pi. There's going to be a lot of sort of getting familiar with the programming on it, Scratch and things like that, and just sort of the workings of a Pi. Pis are really cool because they are like a computer that you can hook up to almost anything. They're little tiny things. They're not too expensive. I mean, they're certainly less expensive than like a desktop or a laptop computer, and you can use them for all sorts of different tasks. I say that, and of course, you always have a hard time thinking about specific examples, but really, your imagination is the limit. I had one at one point that was actually just set up to email me because they were doing a lot of work to the transformers nearby my place, and so I tended to lose power often, and it was set up so that it would email me anytime my power was back online, which was a really simple task, relatively speaking, and certainly something I could have done with a less powerful thing than even a Raspberry Pi. But a Raspberry Pi, actually, I was speaking with my boss today at my other job, and he spoke about how he's interested in aviation and how Raspberry Pi is a computer, actually. So that's the other thing. It's a whole computer, including an operating system and stuff like that. So it's got a distribution of Linux on it, which is Linux is a generally, depending upon which flavor you get, a free and open source operating system. It can be exactly much cheaper. But yeah, it is an entire computer. And so anyway, aviation. One of the most expensive parts about getting a plane and operating a plane is the avionics in it, the GPS and the navigation system and the altimeter and the communication system and all of that stuff. Well, there's a guy out there, and I can't remember his name right now, but he actually introduced his own open source avionics software, and you can basically hook up a few Raspberry Pis to a couple of industrial LED screens and get the buttons that you need and everything like that, and hook it all up, and you have an avionics system in your airplane for, let's say, $200 instead of $90,000. So things like the Raspberry Pi, like I said, your imagination is the limit. You can either make it to send you an email when the power turns back on, or you can make it to control all of the electronics and all of the navigation and all of the communication and everything on a plane. So that's pretty impressive. That's a pretty wide range of applications for it. Oh yeah, what's up, Kevin?
Technically, the Raspberry Pi is not a entire computer. It does not have a BIOS.
It does.
So yeah, take out the memory card and put it in a separate computer to load up any OSs.
This is true. But if we're speaking in technicalities, a computer does not necessarily require an OS. A computer is just a thinking machine. So in that sense, a Raspberry Pi is a computer. You've got a computer in your car. It doesn't necessarily have an operating system, but it does do thinking for you and stuff like that. So sorry, I muted you. Does that clear things up a little bit?
Yeah.
Cool. All right, excellent. All right, so yeah, so we're going to be going over the Raspberry Pi. We're going to be using something called the SenseHat, which is you could if you want to elaborate a little bit on this as well, Mr. Dubick, you're more than welcome to.
Yeah, it's Mr. D again. This is used, the AstroPi. It's now called the SenseHat. They use them in space. This has got a case on here. Whereas it's just kind of the board. But what's great is it gives the Raspberry Pi, like you can measure accelerometer with it. It's tilting on it. You can make games on it. It's just a really cool add-on. Just like Arduinos have shields, Raspberry Pis, a lot of times they call them hats. Well, clip on top of the Raspberry Pi and just extend its capabilities. We have a simulator which will allow to use it. The British kids have sent these up to the International Space Station to study space. And we're really excited for you guys. When you come to Collab the first time, you're going to get these, take them home, and then we're going to be able to do the Raspberry Pi at home as you're doing this on the webinars. And one thing you really got to understand, if you haven't used the Raspberry Pi in a while, they have really got much more powerful. They can browse with them. You can use them like a full-fledged computer. Can you play computer games on it? Not so much. But most of the time you use a computer, it's to check your email and do spreadsheets and simple things anyways. All right?
Yeah, this is true. It does a lot of the things that, yeah, it won't play necessarily the latest 3D game. You know, it's not gonna. Well, I'm trying to think of examples here. It's not gonna do like Dota or something like that, or it has some issues with Minecraft as well. There's a Pocket Edition specifically for the Pi, but
that we can hack. That's the best thing about it. It's open source. We can change anything.
Yeah, exactly. You can actually. One of the projects I want to do is I want to get a Raspberry Pi myself, and I want to hook up a joystick and some buttons to it and a screen and turn it into an emulator for a whole lot of classic arcade games and things like that. So while it won't do new games, it can do older ones pretty well, and that would be pretty cool, I think. But yes, the SenseHat, pretty awesome. What is it, like an accelerometer and a few other things?
Yes, accelerometer. It's got a tilt scale. Well, they can do that with accelerometer. It's got a whole band of LEDs that we can program, so we can make a Tetris game on it. Nice. So we've got a lot of really cool things. You're going to see what we'll do is we'll save some of this for you down the road on it. All right. Yeah, it plays games. Yeah, Jasper just jumped in there and said that. Thanks, Jasper. And then the next thing we have on up is to show you how powerful this Raspberry Pi can be. You were talking about computing. We can tie it into artificial intelligence and tie it in actually into Watson. And Watson was a computer that won the chess match. Is the most powerful, one of the most powerful AIs at the time. Now there's some other companies out there that have got them, and it used to be known as Deep Blue. But if we take it, we can go to Watson, and we're going to make that use the same Raspberry Pi, and you're going to be able to program that and access Big Blue, huge artificial intelligence, all on what's basically a $40 computer, which is mind-blowing.
Yeah, that's crazy. I mean, that's one of the biggest things about computing. One of the biggest sort of breakthroughs that's happening in computing is the compute. Well, the computers are still themselves getting stronger and faster and more powerful. It's the ability for multiple smaller computers to interact and communicate more effectively, which is really becoming a big thing in computing. You know, if you can't make the computers themselves smarter, what happens when you hook up a bunch of computers that in themselves may be less powerful than a single desktop computer, but have the ability to compartmentalize their tasks and talk with one another? Well, you get essentially like what's going on with what people do with supercomputers today. Supercomputers a lot of times are just a whole bunch of computers that all have one task that they're all working on over and over again, and they're all talking to one another. So it's becoming much more accessible for that sort of thing, and that I think
It's getting.
is
Go
pretty.
ahead.
I just think that's pretty interesting. Go ahead, Mr. Dubick.
Yeah, I think it is too. And you can tell we're at two locations, guys. And just think of the technology that we can all teach from the best of both worlds, be at different locations. But to get back to what Mr. Detoy, Tom's saying, we've gotten the prices computing goes down to the Moore's law. Now we're moving towards free. It's getting cheaper and cheaper that you can embed it. And that's what we talk about with physical computing. They're now making Arduinos. This is another thing that we used last year. They're selling those for $7. Those used to be 40, then now down to 24. They're now to 7. So if we're making them cheap, that means then, and we're connecting them all across the network like that, will be doing things you can't even imagine in 10 years now. We haven't even thought of, to be honest with you.
Oh, there you go. By zero W for $10. Oh, we're going to be
Yep.
going back into computer aided design, or CAD, if you've ever heard of AutoCAD or Tinkercad or any of those programs. That is computer aided design. So that's making stuff in 3D with a computer, designing things, hence computer aided design, or just making art. And there's a whole bunch of different flavors of those. I mean, obviously, we're going to be sticking more to the engineering side of things, although it's going to be a little bit more accessible, I think, since computer aided design, CAD stuff, can get pretty hairy and pretty involved. Um, so a lot of times it's better to get a sense for how to do these sorts of things with more accessible programs, just so that you know what you're doing when you get to the more maybe complex stuff later on in life. So we're definitely going to be covering that as well, and that's always interesting. And we're going to be programming with Python. Python is a fantastic programming language. It's very easy to get into because it's very close to the English language, certainly compared to a lot of the more archaic programming languages that exist out there. If you've ever programmed in C or assembly, whatever type of assembly it may be, or once I programmed in binary, I don't recommend the experience. It's not fun. C sharp. C sharp is a good one. C sharp is a very object-oriented language, and it's a little bit less sort of English native than Python is. You'll actually be surprised once you get into Python if you've had experience with C sharp. Um, and the conventions take a little bit of getting used to at first, but then you realize exactly how high level the language is, how much you can do with a small number of commands, and it's pretty interesting. It's a very good language to learn on, so that'll be cool. Well, it's not bad necessarily, but it can be confusing.
And let me jump in on this. So we are going to, if the real trend of this fall will be the Raspberry Pi and then getting into Python and then utilizing all these things. When we're going to also have quadcopters, you're going to learn how to program the quadcopters using another language besides not just flying it with a joystick. So we have some custom programming you'll do with that. Real quick show of hands, because so we know how much time we need to spend on this to get people introduced to programming. How many people have done Scratch or some kind of programming already? Please raise your hand. We just want to get a quick sense of this. All right. Now we have some people, so, okay. Let me do it and ask it another way just to make sure people are still listening to us. But raise your hand if you've done no programming. Totally cool. We'll take you from getting. Raise your hand if you've never done any programming. All right, fair enough. Okay, so don't worry if you've not done programming, because we got 25% of us have it here. That's great. We'll spend a couple nights in a language called Scratch to get you up to speed. Those of you who have done Scratch and done some other programming, we'll challenge your Scratch skills and try to get you to do a little bit more than maybe you haven't done. So, and it's just a good refresher. Scratch is an icon-based language, easy to learn, but I would like to make everybody understand this. It was developed by MIT to teach programming. Harvard freshman programming students start with Scratch. So it can be really great for teaching the fundamentals. Would you agree, Mr. Detoy?
Oh yeah, Scratch is fantastic for that because you don't have to get, like, sometimes the syntax can get confusing and dissecting your logic. Maybe you did something weird with the logic and that's why it's not working. Maybe you misspelled something. And so being able to sort of remove that whole aspect of making sure things are spelled correctly and stuff like that, and just purely focusing on how a program flows and being able to look at it in sort of a visual way makes it a lot easier to figure out exactly how a program is structured.
Agreed. All right, yeah, go MIT, absolutely. Now, let's talk about what we're going to do at the Fab Lab. Although this will be primarily me, but we also have another person that I think Tom Detoy would hit it off with. Hopefully you guys will get some time to work together. His name's Will Rudolph. He'll be joining us on some of the fabrication. He has got a lot of experience in woodworking. Some of you met him this summer, but we're excited to get him involved. So we will do, I guess we'll be doing this online, but we'll be doing some digital portfolio work so you can record it. I can't stress enough. Save it, write a little bit in your digital portfolio. You'll thank me later when you're applying for college, and then you can show that, hey, even in the 7th and 8th grade, I was doing engineering stuff or coding stuff if you decide to go the programming route. And that's one cool thing about what we're doing too. If you find as you do this, you go, you know what? Making stuff's great, but I really like the coding more. Then you know where to be looking. If it's, I can do the coding, but I really like making it, then you know, hey, maybe you need to be more on the engineering side. But I would make an argument, and I think Tom would agree with me, all programmers should do some digital electronics so they understand that side of it.
Oh, yeah.
And all engineers cannot be engineers without knowing programming. You can't operate. That's the world we live in.
Yeah,
all right.
Yeah.
We'll keep doing computer-aided design as it applies to what we're doing. We're going to do computer-controlled cutting, which would include, vinyl cutting, laser cutting for that matter. We'll tie in with that. People still like to do some 3D printing. We'll include that. We have electronics. We have a project that you'll all be doing together in the middle school. Let me raise your hand on this next question. I'm going to put everybody's hands down. Raise your hand if you made an LED desk lamp with me this summer, or with Will, with us. Did you make the LED desk lamp? Okay, great. That's a project we're going to do. You're going to make your own. It's a really sweet deal. You're going to see how the wood comes in, how we flatten and square it. Then we're going to add electronics to it. And it's going to be really, really, I think you're really going to enjoy it. It really comes out looking cool. So that'll be a combination of laser cutting, using a router table, which is not something everybody starts off the bat doing, and doing electronics with acrylic, and using a table saw. Don't worry, moms and dads, table saw is meant in such a way as not to, it can't cut your fingers. And we'll be standing right over the kids to make sure everybody's safe and they're just having a great time. We'll also, because you've got electronics, we'll be doing a little working with our Raspberry Pis in that regards. But we'll let you know when you need to bring them. Now, for the next thing, I assure you, being a Fab Lab, with all the equipment we have, you're going to get to do a lot of interesting things. For example, the LED desk lamp, it has embedded computing in it. It has lights. You're going to be able to change the lighting, programming, and the whole 9 yards of those. On 3D printing, we tend to, in the lab itself, we use 3D printing, but it's just one tool of many. I'm sometimes guilty of remembering a lot of students don't get to use 3D printers very often. So we'll make sure everybody gets to use it to make something they want. They made something last year. I challenge you to make something a little more complicated. Then, new woodworking tools. We got a router, we got a planer, we got a joiner. So you can take wood from a sawmill, run it through these pieces of equipment, and have finished wood that we can then make, furniture out of it, or we can make, for example, that LED lamp. And so when this all comes to goes, you get to make all kinds of things are made here. This is all made out of cardboard with lights that are programmable. It was layered after layer, so it was a really beautiful art project that was done. I teach this stuff all day long. I can't get enough of it, so I teach, obviously, get to work with you great kids. So right here, this was done with a topography map and a CNC machine. So that's something you might do in the spring as we learn more and more skills. Last year, kids made guitars. That's a guitar hanging in the Fab Lab. When you come into the Fab Lab, you'll see it hanging there. Here's a robotic can. And this is why you want to have a digital portfolio. This is one of my students, and he's controlling that robotic arm with his arm, just as we do to help people that are got a challenge. Our veterans that come back maybe from the war missing a limb. He was able to pick up that glass, doing it that way, which is pretty amazing. And depending how fast we go, we'll keep doing projects. Grading and homework. Okay, that might have been, oh, whoa, man, whoa, here we go. Sorry about that. We said this earlier, not going to try over. You don't have homework per se, unless we ask you to do something we didn't get quite as far in class or you're a little behind. Try to make it up there. We're not going to grade your class in terms of, oh my gosh, you've got to work hard to get your A. You get enough of that in regular school. But it is up to you. You're going to get so much more out of it if you stay current on the webinars. Because Tom and I are teaching these webinars. Then when you come in the lab, you're like, hey, I've done Inkscape or I've done Python, so now I know how to get working on this. If we have to teach it from scratch, it just slows you and everybody down. So we just covered a lot there. Do we have any questions? Raise your hand if you've got a question. Natalie. All right. Natalia, got a question?
Yeah.
Yes.
The PI. So the 3 USB ports, what can you use those for?
Oh, the Raspberry Pi, what can you use the ports for?
Yeah.
Sure. Well, one, we can use them. I'm going to mute the answers so we'll keep bouncing back and forth. You can use them. First, you need them to hook up your keyboard and mouse. All right. But then you can also use that USB part to connect to other things, i.e. an Arduino. So you use them like you would do anything that connects up to USB. All right. You can use it as a power supply if you really wanted to use it that way. Did that make sense to you?
Yeah.
All right, great. Anybody else have a question about what we're doing? Is there anything that people really wanted to do this fall that maybe we didn't mention or you thought we were doing and it wasn't mentioned? All right. I got time. I think you're clicking. Is there something you want to add?
Whoops, nope, totally forgot that that I had mouse control. I just went and checked through to see if there were any hands and then moved it back to a neutral position. Didn't realize taking control of you again.
No worries. I just pick it up so we got it. Now, also too, I might add, we're going to try to always end by 55 till. So that way we have time to get ready for the next one, all right? And we'll be sensitive to your time. We'll try really hard not to run late. Okay, Tom, do you mind taking over for the next 9 or 10 minutes?
Yeah, that's fine by me.
I'm going to check the emails and then make sure if somebody couldn't get on tonight and take care of that. Folks, I'm really looking forward to you, and I will be getting to work with you Monday. So take care, guys.
All right. See you later, Mr. Dubick.
You bet.
I'm just going to go ahead and make myself presenter.
And mute me.
Okay. So welcome over to my computer on a totally different operating system, just to keep things interesting. Yes, I remember that, Liam. Yep. All right, so this whole sort of area is devoted to the difference between science and engineering, because I mean, you guys get taught the scientific method a lot of times in school, especially right around now in early high school and stuff like that. Actually, I remember hearing about it in elementary school too, especially with science fairs and stuff like that. You get taught a lot about the scientific method. There is an engineering method as well, and there's similarities, but certainly differences between the two. So why don't we spend some time going over them? So what is science? Well, Webster's dictionary defines science as knowledge or a system of knowledge covering general truths or the operation of general laws, especially as obtained and tested through scientific method. Basically, the stuff that we know that we can prove that we know, beyond a reasonable doubt, given the knowledge that we have. So based on the stuff we know, what stuff do we know? It sounds a little confusing, but it's basically what we know. I mean, we know that gravity pulls us towards the object of highest mass in the vicinity, and we can reasonably say why to a point. We can predict when it's going to happen. We can, if we really wanted to, we could express it mathematically. We know more or less why the sun creates light and heat. I say more or less because when you get really, really down into like the details, like you can ask why forever, and at some point the why just goes like, our only answer is because it's what it does. But that's part of science, is uncovering another layer of the why, pushing back that wall of because that's the way it is. And we've gotten a lot better at that. But so that's science. Science is what we know. Well, what's engineering? Engineering is the practical application of science and math, as in the design of and construction of machines, vehicles, structures, roads, and systems. So while science might be what we know, engineering is more how can we use what we know? So essentially, engineers use math and science to improve the world. So let's take a look at the engineering versus the scientific method, because I was just harping on that a couple of minutes ago. So the scientific method, the scientific method is observation, hypothesis, experimentation, analyzing your data, conclusion, and most exciting of all, peer review. Whereas the engineering method is research, plan, prototype, and commercialize. So let's dissect these really quick. So the scientific method, observation. You look at something, you go, interesting. There's a fire that's created every time I hit, flint with steel. That would be your observation. You notice something that's happening. Your hypothesis would be the why that's happening, or what's causing that, or whatever. Hypothesis is, okay, it's because the flint is full of angry ghosts, and whenever you hit it with the steel, it frees them, and then they fly all over the wood and start a fire. So you experiment. You try exercising the flint. You try throwing it into holy water. You try using a medium to figure out what exactly is going on. If they can talk to the ghosts inside of the flint. And then you analyze the data and you go, well, none of those things really worked. We tried exercising it, nothing changed. We tried throwing it in holy water, nothing changed. And after it dried off, it still created sparks. We tried having a medium talk to it, the medium couldn't find anything. From that data, you arrive at a conclusion. Your conclusion might be, hey, maybe flint isn't actually filled with angry ghosts. Maybe there's something else going on. So that's the point at which your scientific method might start over again. Observation, hypothesis, experiment, analyze data, conclusion. Peer review comes in when other scientists come and look at your work. They basically look at everything you've done. They look at all of your evidence and everything like that. They try and repeat it and see if it's reliable, because maybe in your efforts to find a suitable medium to speak to the flint, you found somebody who just wanted to tell you whatever you wanted to hear. And you go like, oh, okay, so, or maybe they honestly thought they heard ghosts inside the rocks. And so when you say, hey, so can you talk to it? And they're like, yes, they're telling me that rock life is very boring. And maybe the whole idea of throwing it into holy water, maybe that was enough for you. You didn't wait for it to dry off because as you hit it with the flint, it didn't create sparks because the rock was wet, and you thus concluded that you got rid of the ghosts inside of it, and so now the flint is inactive. This was an incredibly bizarre thing that I created off the top of my head, but the example still holds. So peer review in that case would be other scientists coming and going, okay, so let's dunk it in holy water. All right, so I see so far that makes sense. However, if we wait for it to dry off, it still creates sparks. So we can probably reasonably conclude that their conclusion about holy water is probably not correct. That sort of thing. You want to make sure that your experiment is repeatable with reliable results before you can really start to say that whatever endpoint you've arrived at for this particular experiment is reasonably correct. So that's essentially the scientific method. Then you got the engineering method. Well, you see. So the engineering method: research, plan, prototype, and commercialize. Research is, well, let's say you wanted to make let's see here, a machine that put angry ghosts into flint. Let's say maybe we determined that that was a thing that actually happened. So research is you figure out how this can be done. You say, okay, so what are all of our possible avenues to cram as many angry ghosts as possible into flint? Well, let's see here. We can try, I don't know, we can try, method A, we can try method B, we can try method C, we can try method D. No more ghosts? Okay, no more ghosts. Let's say you're trying to make the best plane ever, since we were talking about planes earlier. You're trying to make a plane that flies faster on less fuel. So you've got, you guys are giving me conflicting signals here, all about the ghosts. You've got different sorts of plane designs and things like that can be used for your more fuel efficient and faster plane and things like that. So you've got a number of different avenues to explore based on different things in the scientific method. Maybe they found that a new swept wing sort of design on a plane based on some sort of weird adaptation of Bernoulli's principle and thermodynamics or aerodynamics and things like that. Maybe thermodynamics too, who knows? The wing works better than wing designs that currently exist on planes. So the engineering method in this research, you would pull from that sort of new scientific discovery and go, hey, this is a possible avenue to explore. Then you've got plan. Plan is where you take all of the different options that you've created and that you've collated in research, all the different things. Okay, so maybe if we make it out of this material, what would be the pros and cons of it? If we made it out of this material, what would be the pros and cons of it? And then narrowing it down maybe to your best possible option. Okay, so we're going to go with this wing design. We're going to use these materials. We're going to do this, and this. This is going to be our plan. That's where you get to prototype, which is where you actually build a reasonably working replica of your idea. So anything that you come up with in plan, this final product, theoretically speaking, you would then build a prototype, which is basically really only meant to display that your plan works. Now, this is the point where things can repeat in the engineering method. You can go between prototype and plan and even maybe fall back to research who knows how many times. Just like up here in the scientific method, you can go from conclusion to observation or conclusion to hypothesis or conclusion to experiment. You can go from prototype to plan to research to plan to prototype to plan to prototype, so on and so forth, over and over again until you've got something that is a viable prototype. Now that last step, commercialize, I could make the world's most amazing, awesome plane. But I'm the only person who knows how to make it. I'm the only person who has the tools to make it. I'm the only person who knows where to find the materials to make this plane. It's only available in some obscure mine somewhere in Central America, and I have to fly down there personally every time and go mine and, a whole bunch of it and then get it carted back up by boat, and I'm the only person who has any control over this thing. Well, that's just a horrible commercialization plan. You want to be able to make it so that this is widely accessible for people. You want to reduce the costs of building it. You want to reduce the amount of materials required in order to make it. You want to be able to make it faster. You want to be able to sort of standardize the creation of it and distribute it. The plans to make it around the world and things like that, so everybody knows how to make it and they're able to. That way, you can. Well, I mean, it's a little bit cynical to say it like this, but you can make a profit off of it because a lot of things, while people will pay for them to be made en masse, if you can create a system in which your whatever you've made adds to the economy, well then it will take off on its own, and it will establish itself in the world, and other people will take up the design and make it, and soon enough, suddenly people all around the world are making my superplane, and it's being used for all major airliners going around the world, and the fuel crisis is no longer a thing, and the looming fuel crisis is no longer a thing, and everybody can get from Georgia to Austria in an hour and a half, and the idea is that would be how you would affect major change in the world with whatever you've made, is the ability to make it so that everybody can make it and distribute it. At this point, it is just about 7:55, so I want to leave it open for some question and answer, and we'll also get started on the poll questions because that will be good practice for the rest of the semester. I'm going to ask you guys a couple of poll questions at the end of each class. I want to make sure we at least get like 80% response. It gives us some idea of how we did with the class that day, and what we can do in the future and stuff like that, and then leave it open for question and answer time as well. I'll generally try to end it about 7:50 so that at least you guys have a couple of minutes for questions. But yeah, so we'll go ahead and do the poll questions now, and then we'll break for Monday, and yeah, and then we'll meet up again on Monday. So here we go. First poll question is incoming. Just go ahead and pick an option, hit vote. It should take up your entire screen. Let's see if we can't get a couple more people to vote on it. All right, we're at 82%, so 5, 4, 3, 2, 1. Close. I should also say that this is totally anonymous, so if in the future you really do think that there was something wrong with it, you're more than welcome to vote that. Don't think that there's going to be any sort of like retribution or anything like that, because we're honestly interested in making sure that this is the best experience for you guys as possible. Okay, gotcha. But if you ever feel like there was something seriously wrong with it and you feel comfortable coming to tell us, please do, because it's more important that we know what we can improve upon for later. Here's the second one. All right, 82%. So 5, 4, 3, 2, 1. Close. All right. More or less, the pacing was good. again, if there was any part that really, like bothered you, feel free to let us know. And that is actually going to do it for today. We got a couple of other poll questions that we can ask throughout the rest of the semester, but for today, those two really aren't applicable. So we just got two. All right. So that should do it. Y'all have a wonderful weekend. We'll try and maybe pick up. Maybe we'll jump right into the semester. We'll see. But you guys have a wonderful wonderful weekend, and Mr. Dubick will see you on Monday, and I will see you on Wednesday because I'll be doing Wednesdays and he will be doing Mondays. So yeah, there you go.